So I work as a research engineer at Safran, which is the corporate research center of the Safran Group, which I'm going to quickly introduce on the next slide. But first of all, I would like to thank the organizer and especially Kirby for having me there. I think it's a very nice community that I'm discovering. Obviously, this opinion may change depending on the question that I get at the end of the presentation. So you can say that I quickly changed while preparing the slide, the machine learning part to what a funny colleague of mine called glorified regression, because actually what I'm going to present is, I think, not rocket science, especially in your community, which is quite ironic because my employer does rocket science among other things. So just a few words about Safran. It's an international company, rather large company, which employs about 90,000 people, half of which are located in France. And it's a company that designs, manufactures, and sells quite a wide range of products. We are mainly known for aircraft engines, but we also operate in the defense sector, for example. And we do, say, sub-brand optics sometimes. And the way I like to present the group is that all in all, in order for Safran to keep a competitive edge, the products need to be improved, and these improvements require improvements in terms of manufacturing processes or materials, which places material science in the right spot, even in this kind of industry. And you can see that some impressive number about the research dynamic in the group. So, as I said, I'm going to talk about computational structural alloy design, and I figured that in order to introduce the three illustrations that I'm going to talk about, I would go back to the basis of material science and choose a triptych of composition, processing, so structure and properties. So for a given material, you can do basically process optimization, which means finding the right structure to get the property that you want, because it was said in a few presentations before that it's alloy design, material design is basically an inverse design problem. So you're trying to, you know what you want, and you're trying to either optimize for a given material, the structure, or for given material and processes, both the composition, chemistry, and the process. But there are a couple of issues there. The first one is the combinatorial explosion you get mathematically, and that can be illustrated by considering we went through the edges from binary bronze alloys all the way up to high entropy alloy or complex concentrated alloys, where you can choose 50 elements with a large number of actual level of concentration that give you 50 to the power of 50 possible material. Then you get to handle the complexity of processing. And last time I was at INS last year, we actually computed with a colleague that do PVD, physical vapor deposition, that you could easily reach 10 to the power of 20 different combination of parameters. So it's quite a it's not quite, it's a very naive way of counting things, because a lot of that's parameters that don't work, but the point is there. And these two numbers combined, and you get completely combinatorial explosion. And then there is a space of properties that you have to live in. And actually, properties, in terms of physical properties, is maybe the easiest part of it all. And as an industry researcher, we know our products, so we know the performance we are expecting from them. But we have to comply, like our material design program, with compromises, which include a lot of other considerations. So obviously, we have to be cost efficient and time efficient in the production of these materials. We also talked about sustainable development. So you have to think about repairability, maintenance. Safran is not selling engines, it's selling engines availability. So if an engine is down, it's on us. So we have an economical interest to have very easily repairable engines. And then there are regulations, which we talked about yesterday, is one of the main driving factors, either by trying to find alternative alloying elements, or by trying, and this is the context of the presentation, material with higher temperature capabilities or lighter materials, so as to increase the engine and reduce their greenhouse gases emission and noise emission as well around airports, which are really two main factors. So around this graph, I'm going to be talking about design of high temperature titanium alloys, amongst other things, which doesn't consider the structural parts, which may seem like suicide in materials setting, but bear with me a little. Then I will talk about the design of an aluminum alloys for additive manufacturing, but from the optimization of the process point of view. And then I will focus on information detection in documents in order to feed the supervised machine learning model that we use all the time. So why are we interested in high temperature titanium alloys? They fit in a space between say, steels, aluminum alloys, and high temperature nickel based alloys in terms of high temperature capabilities. So we're talking about 500, 600 degrees Celsius applications. Applications that are either outside the engines. We're talking about the exhaust that see the hot gases from the combustion that are out the turbine. Or we're talking about in-engine application, basically the high pressure compressor discs that are subjected to very high level of mechanical loads due to high rotational speeds, for example. And the context of this study was actually to find an aluminum, a titanium-based alloy that was less sensitive to a particular form of fatigue, which is wet fatigue, which leads to very premature rupture of the disc that causes an incident a few years ago. So the playground is the periodic table of elements, but if you keep being naive like me for a few minutes, and you look at the element that you can choose to combine to create an actual titanium alloys, according to patents from the onset of titanium alloys up to a few years ago, you can choose about 45 elements. That doesn't mean you have to put 45 elements in your titanium alloys, but you can. And that gives you a combinatorial expression that I already explained. I always like to express the edge of the universe in octosegons, because it gives you a sense of the craziness. But obviously that's not the space that we consider when actually doing the project. So the actual playground was revolving around the, let's say, the outskirts of a commercial alloy, which is called TI6242S, to which we added niobium, and the idea was to minimize the number of combinations that we had to consider. But the problem is that we didn't have any data to start with. So what we did, we had a two-phase project when in the first phase we did some naive alloy design to generate data to the model and then to use this model to optimize the composition of phase two alloys. So we do a lot of calculation of phase diagram in this kind of materials because the database are commercially available, and it makes sense to consider equilibrium calculation for high temperature material, because during their service, they tend to adopt actually the predicted microstructure. So I'm not going to go into too much detail. The idea that we don't consider these results calculated as absolute results. We use commercial alloys as reference, and we try to compare the result of calculated with that of the commercial alloys to identify alloys that are less sensitive to fatigue, for example, as expressed by a number of criteria that we relate to phase diagram. So we manufacture 14 alloy, 13 alloy, the last alloy is TI6242 for reference purposes. And there is no structural optimization. Every alloy is treated the same way. So that's a real keep out there. It would be just too complicated to customize the treatment form. I'm going to go through just 2 slides of results, and I think the most interesting one actually is this graph. So it's the results of tensile testing at room temperature. It's far from being the only thing that we did. And what is plotted is the ductility difference to T6242 as a function of the ultimate tensile stress difference. And so ideally, we would like to be here to material with better ductility and resistance. But you can see that the 13 alloys actually didn't beat the physics behind resistance and ductility. If you gain resistance, you lose ductility and vice versa. This is basically what it represented there, but there you can see that generally we found some alloys with better actual resistance. We also did study the oxidation behavior. The idea there, it's another part of the compromise, right? Is to this time be on the left side to minimize the mass gain due to the intake of oxygen in titanium alloys because they love oxygen. So either judged by the mass gain or the parabolic constant of oxidation. So 2 ways to judge the kinetics of oxidation. And we evidenced some obvious compositional dependency on the delamination, the thickness, the composition of oxide layers with the key influence of silicon. But basically we found rather reasonable observation that didn't contradict the literature. So that's where I commit suicide in life. So we talked a bit about small data, and we talked about the fact that, and we'll come back to that in the conclusion, material sciences data pool. I would say structural alloy design is even poorer because the actual experiments are very expensive. So we tried to build model using 14 data points. Obviously, it's not neural network, it's not deep learning, it's just basic linear regression with feature selection in order to simplify the model at maximum model. So the idea that we got some, I would say, moderately predictive. Predictive is a big word there, but models for which the Q2, which is kind of a cousin of R2, was sufficiently high for us to believe that the model would guide the design in the correct direction, which is what we did. So what we did in the phase 2 was to use the model that we built to guide the optimization in the envelope of the experimental composition of the phase 1 alloy. And so it's still quite a big space, but we had to choose 2 alloys for larger scale production synthesis. So with the genetic algorithm utilization, and maybe I could answer a question that we might have. No, we don't need to do a genetic algorithm there because we could just screen the whole space using linear models, which is not just at all. But I had that prepared, so I did that. I'm not going to go through the working of the algorithms. You basically feed a multi-objective specification optimization problem, and it gives you a variety of different compromises. The idea there is that we tested the same way these phase 2 alloys as compared with the phase 1 alloys. And what we found here is it's approximately the same representation as before. You have the ultimate tensile stress or yield strength difference relative to TI6242S. You can see that it works quite well up to 550 degrees Celsius. Then it all goes down, either in terms of resistance or in terms of ductility. So it doesn't work at a specified temperature, not as we wanted. But if you look at the same picture, same graph as before, the position of the two phase 2 alloys is actually quite good. I will say it's really exaggerated, but we kind of beat the physics there by having alloys that are more ductile and more resistant. Doesn't work at all temperatures, as I said. And what's interesting about these alloys is that we work with Steinmetz on them, so with the head of research of Steinmetz, Europe, and we could, well, experts of titanium alloy could explain why those two alloys could work, but coming up with the actual composition in the large composition of space was not obvious, and I think that's really the point of machine learning. Machine learning, glorified regression with popping data points. Onto the aluminum-based alloy design and process optimization. So we're in the context of finding what we call high temperature aluminum alloys. So we're not talking about 500 degrees Celsius, we're talking about 150, 200, 250 degrees Celsius application. The context is also additive manufacturing, and you can see the kind of specimens that technological specimen that could be built to include, you can see it's a notch there that creates a stress concentration. And the idea is to provoke cracking and to judge the processability of the alloy using additive manufacturing as a function of the crack length. But because of you don't build actual parts with notch like this. So just a quick recap on how we designed these alloys. Before I came to Safran, one colleague of mine used about 50 data points on ultimate tensile stress to guide the choice of alloy universe and their concentration towards a region that I couldn't pinpoint in my files. So I put a big point. But the idea is that behind those two fake axes, in reality, that's UTS at room temperature and UTS at 300 degrees Celsius. And the colleague just maximized both of these quantities. And so obviously he had some problem considering the specimens because of insufficient ductility. So what we did was design of the phase 2 alloys that we aimed at something that was much more reasonable in terms of UTS. And that works quite well. And once this compositional optimization was done, we went on to do process optimization. So basically trying to customize the power of the laser, the speed of the laser, and the distance between the laser and the building plate. And this is a result, kind of like a result that we got. So this is the porosity surface area that is measured when cutting in half the specimen. That gives you an idea on how porous the material is, how dense it is, represented as a function of a post-fabrication crack length when the stress are relaxed. So the different colors there. So you see that the triangle and the square, they're actually the first specimen that were the first set of parameters inferred by material experts and AM experts. And so we used these data to build a model of crack length and porosity area as a function of parameters and try to optimize both of them to reach the ideal point of 0, 0. So you can see that we started from something that was fine in terms of porosity, but not fine in terms of crack length. Then, if you look at the you can see that the use of the model led us to the opposite. So we're cracking length, but we're not fine in terms of porosity. So we added that this data onto the whole data set. We did the optimization and found these points that lie at the inflection points of the curve. And actually, when we included that in the new models and did multi-objective optimization, p-objective optimization, we found this Pareto front, and I think we arrived about here without finding an ideal solution. But that wasn't completely unexpected, given the very harsh the technological specimen that we had. And once again, just like titanium alloy, I think it was very interesting to have the human in the loop in between each step of optimization to guide the selection of process parameters. Just to give you an idea of this alloy, it's quite a fun alloy. If you look at the tensive stress, the anti-tensive stress, measured at different temperatures as a function of the heat treatment or the etching temperature and time, you can see that if you look at the measurement at 20 degrees Celsius, that even after 500 hours, 300 degrees, which was really hot for aluminum alloys, the material keep its strength because of its precipitate strengthening. It's very particular aluminum alloys with a lot of titanium category. Everything is public. You can find it on the internet if you're interested. It's also a very high ion modulus alloys with a specific modulus that is 20 to 25% higher than Ti64, even at 400 degrees. Then I'm going to talk about information detection. This is somewhat a hobby for me, because experimental validation is very costly and not time efficient at all. So I have to do something else while competent people test the material that I predict. So why interested in patents as all documents? The reason is patents are quite rich documents. Are quite rich documents which contain a lot of information regarding composition tested by companies or by academics. It's rare. And I figured I would start considering patents because, yeah, because they're supposedly written by jurists, which should follow rules, formatting, regulation, and then titanium alloys. I thought they could be written in like 3 or 4 ways, and I'm going to show you why I was expecting them to be simpler. But so patents are very interesting documents, yet they're very hard to analyze because they oftentimes time documents because there is handwritten comments all over the place sometimes, or just at the last pages, but it's this. So you can't do optical character recognition. Their format is all over the place, and you have time to look at what I call the 50 shades of TI64, because this is all TI64. this is the same composition. So even if you add the actual text, you need to create rules to identify that as being a single and only one composition. The idea there is to use computer vision and deep learning, but not very deep learning, to be honest, to go from object detection, which has been really advancing, fast advancing field for the last 10 years, and do page object detection, and to use exactly the same kind of algorithms, and try and identify the relevant pages that you have to ask an expert to go and see and extract the information. So we're talking about information detection. We're not talking about information extraction. Because my point is, it's much easier for an expert to, in the blink of an eye, identify which part is relevant in the document. But the information is very diluted in general in large corpus of documents. I thought that was a 1-year project, and once I ended the project, there were about 200 new Chinese patents that I would have had to actually analyze. So that's kind of the mindset. So we had an introduction on semantic segmentation for Minecraft. This is exactly the same process. What we give to the algorithm, that's a public algorithm for line detection in historical documents. You give it semantic segmentation, highlighting the composition of titanium alloys, and what you get as prediction are probability maps of each pixel being of the class composition, or being of the class everything else. It was a two-class problem. And that's actually works not that bad. That's a work in progress, but we're talking about 3 million parameters unit-based models. So it's not a very deep model. It's not pre-trained. So it doesn't have a very high precision. So the positive prediction can be wrong quite a lot of time. But it got a rather good recall. So when it identified something as being positive, the number of actual composition recovered, identified with this model is quite high. And you can see some example there. That is, for example, they're all false positive, but that is a false positive because I forgot to give it the sum of the actual composition on the page. Then you can find that the algorithm finds some sense, makes sense of what the composition is, because in some patterns it would, that's the actual quality of the image that I gave to the model. It found that a list of elements looked like a composition, or that 1.9 atomic percent of other alloying elements, something like this, alternative alloying elements, looked like a composition, which is the case. And then sometimes it got completely wrong prediction, but that was really not the case for most parts. So, got 30 seconds to finish. So as I said, I think the two examples that I showed you about titanium alloys and aluminum alloys shows that the machine learning or glorified regression can be of help to guide the design of composition or process. If you're interested in this kind of work, there's been considerable work at Safran nickel-based alloys for this kind of turbine blade. We've produced approximately 60 alloys using this methodology over 5-year periods, which are alloy performance, which is quite competitive with, say, General Electric research. We characterize this material through the production of about 300 kilos of materials, which is really not a lot considering other type of developments at that point. And I would like to expand on what you presented yesterday with the idea of a unified foundation model to combat the what I got, but I did that yesterday evening, so that might not be my best contribution to this session, where I got a small data course, because in general, working on anything else but thin films, so large bulk structural alloys, means that you have to conduct at one point or another very time-consuming and expensive experiments, which means that there is a clear imbalance between the time you spend in numerical simulation and the time you spend doing experimental validation, which is this is the real-time ratio that I observed. So you have few iterations of it for two reasons, because project managers want to see results in the shortest time possible, and iteration. So most of the time there's no iteration, and we do one-shot design, which is an error. Really. And so there's two data gathered by projects. So you've got this tiny island of knowledge throughout the composition of space that somehow we would like to link, because there is a physical continuum behind all of that, and that is kind of what I would like to explore. So, thank you for attention.
Okay, I think we can take one very quick question. Yeah.
So one of the problem you optimize simultaneously 8 properties. So do you think that some of the property we conflict so that it maybe makes the problem have no solution? For example, because when we optimize alloys, when we increase some property to some extremes than the other, so
that's the case in this case. Of course, the case. Typically the mechanical resistance is uncharacteristic to oxidation resistance. Clearly.
Okay, so how about just fix some property and just optimize
That's
the other?
basically what we came to do.
Okay, okay. So one quick question, the objective is to optimize the property for working in high temperature around 600 degrees, more than 600, but also data set you consider the experimental data from 20 to 600. Why you?
Because that can be antagonistic as well.
So,
you can have very resistant alloy at room temperature that are bad at high temperature and vice versa. You can have alloy resistance at static loading at room temperature that are not good in fatigue at high temperature.
so
Can I suggest that this is continued over lunch? I think there's going to be a few more questions here.